Hello, thank you for taking the time to watch this presentation. I'm Joseph Casa, and this is the panel presentation I would have made if I had attended the symposium and would be making the presentation in the panel. First thing I had to do when I was asked to do this was to look up what was pragmatism. And I went on the internet and found it's a rule for clarifying the contents of hypotheses by tracing their practical consequences. So my presentation is applying pragmatism to the systems engineering process, and what I'm going to do is examine the consequences of tailoring the systems engineering process. And I'm going to look at the systems engineering process from the perspectives perimeter using the holistic thinking perspectives: external, internal, progressive, and remaining, or at least some of these perspectives. So we're going to look at the systems engineering process. So the first perspective I'm going to look at is the functional perspective. And then I say, well, which process is it? Is it this one in IEEE 1220? Is it this one? Is it this one in the textbooks? Is it this one? How about similar? How about this one? Which process is it? Then we take a look at the different processes which come from the standards and look at how they were done over time, and you find that they don't all cover the same areas. There are some aspects that are missing, including the whole front end. And so think about that for a while and come to the conclusion that these are internal perspectives. The standards were written by people who documented what they did. And this is one of the ways you get things wrong. You document what you observe, whereas you should be documenting what people should be doing. And so, again, we look at the temporal perspective. So what was the result of using the standards? Well, in a United States DoD report on the acquisition of national security space programs, it said, inadequate systems engineering in the early design and definition stages of a project has historically been the cause of major program technical cost and schedule problems. No surprise, the standards don't cover that, so the work isn't being done. But what about this one in 2005, a definite linkage between escalating costs and the ineffective application of systems engineering? So, what is the result of all these standards? Well, my conclusion from the scientific perspective is standards might help you produce the wrong system more effectively. But now let's take a look at the way we teach systems engineering using these standards. Here's the systems engineering process, and here I'm looking at the consequences. Well, this is what we were teaching at the University of South Australia 10 years ago. And I can walk you through this diagram, talk about requirements analysis, I can talk about functional analysis, I can talk about synthesis, and I can go through every single line on that drawing. But what it doesn't do is show how they all link together. And so students will listen to this explanation and they'll nod their heads, and yeah, they understand what I'm saying, but they don't have a clue as to how to use it. And then we talk about the process is iterative. And then we also teach the waterfall. But then how do the standards map into the waterfall? How does that egg diagram map into the waterfall, where you've got the needs identification state, requirements, design, construction, testing, and so on? Well, one of the ways, the way we taught it at the University of South Australia was like this. We would have the life cycle, market requirements phase, concept definition phase, concept validation phase, and we'd show this diagram and the students would look at it and nod wisely, and nobody understood it and nobody wanted to put their hand up to say they didn't understand it. And so I think that there are quite a number of things in systems engineering where this happens. And I'm going to show you one in a moment. But let's go back to those standards. First of all, systems engineering standards are a myth. There are no standards for systems engineering. The standards cover the process for engineering systems, and the standards cover engineering management. And they also focus on the wrong aspect. They don't focus on the front end, and that's one of the problems. However, if you read 1220, section 4.1, you find this wonderful sentence: the systems engineering process is a generic problem-solving process. Is a generic problem-solving process. Well, wait a minute. If it's a problem-solving process, let's see if we can go back to the problem-solving process and see if that gives us a better view, a better understanding of what's going on. And before we get there, let's just take a look at management. Because if you go back here, the standards cover engineering management. And here's a typical one. Look at 15288. This is the original one back in 2002. And you can see it's a list of processes in an organization, and management shows up 1, 2, 3, 4, 5, 6, 7, 8 times. But again, how do these processes link together? And you tell me that you don't use the decision-making process in any of the other processes? It's a standalone process? To me, standards are written by people who can't get textbooks published. So, coming back to the systems engineering problem-solving paradigm, this is based on Derek Hitchens' work, blocks 2 to 7. And so you can see we start with defining a problem space, conceiving the solution options, identify ideal solution selection criteria, then we do a trade-off, we select the preferred option, we formulate the strategies and plans to implement. And as far as Derek Hitchens is concerned, systems engineering ends here. The rest of it is just engineering. So then we go on, we have a milestone at the end here. We implement the solution system. This is the realization process. We have another milestone to say we're ready to test. We verify the solution system remedies the problem. And then we have the delivery readiness review, milestone 12. But let's back away a minute and take a look at the systems engineering or systems development process from the big picture perspective. We have an undesirable situation. It kicks off a series of sequential and parallel activities. These we call the system development process, which produces the solution system, and that needs to be checked to make sure it remedies the undesirable situation. Well, if it's large or complex problems, we call that series of sequential and parallel activities the system development process. On the other hand, if it's a small problem, we call the same set of sequential and parallel activities in concept the problem-solving process. And so large or complex problems are elaborated into many small problems. The system development process uses the problem-solving process, and small problems use the problem-solving process. And so if we talk about it in terms of problem-solving process, you can see how the system development process uses the problem-solving process or maps into it. So now if we go back to Derek Hitchens' systems engineering problem-solving paradigm, you can see that at the end of step 2, we have a clearly defined problem. We then go through step 3, which conceives the solution options, and we end up with a preliminary concept of operations. We move through the process. By the time we get to step 6, we have a final concept of operations, and then we write the requirements during step 7. And this, by the way, is the A paradigm of systems engineering. You can fit the milestones into this, because at the end of step 6, where we have the we've selected the preferred option, we have an OCR, an operations concept review. Milestone 8 is the system requirements review. And then we go through the whole system development, the traditional INCOSE system development process in step 9. We have the preliminary design review, the critical design review, and so on within steps 9. Step 10 is the test readiness review, and step 12 is the delivery readiness review. So the systems development process maps into the problem-solving paradigm very nicely. And it also maps into the waterfall. So what we're teaching now, there are no contradictions between what we're teaching. And we can map this into the waterfall stage like so, and you can show the milestones. And then what I can do in teaching this is I say, well, in the requirements phase, the way we do each of the blocks is so-and-so, so-and-so, and so-and-so. In the design phase, it's conceptually the same set of blocks, but the activities are slightly different. And in the integration and test phase, it's the same set of blocks. We're using our integration plan, but what we do in each block is different. So this seems to me a much better way of teaching the recursiveness of systems engineering. And if you agree with me, leave a note to that effect in the YouTube comment area, or just like the presentation. So, when we go back to the standards, which process do you tailor? Well, the answer is all of them. What do? You create the process that fits your situation using bits from the standards, books, papers, and experience. And that's just not me saying so. I mean, I wrote it in 2005, but Andy Sage and Mr. Beamer published it in 2009. And those are the references up there. You do not fit your situation to one of the processes in the standards. What's documented in the standards or in the books is a particular solution to a particular problem at a particular point in time. Yours is different. You think. You create the process that fits your situation. How do you do it? Carefully. You use thinking tools to develop an understanding of what's going on, what's needed, and how to realize it, both the process and the product. And then you work back from the solution. And you use management by objective to design the processes to define the products at each milestone. The waterfall model provides you with a template. At the end of the requirements phase, you know what you have to have. At the end of the design phase, you know what you have to have. You know what the products are. So you tailor them according to the complexity of the project, how formal they need to be. Do they need to be formal documents, or if it's simple, will a PowerPoint presentation do? Use PAM charts, work packages, and other project management tools to do the job. And you should plan for more than one iteration. And I explain that in the paper, The Nuts and Bolts of Systems, which as I'm saying this, I will be presenting it next month in Norway. But by the time you view this at the symposium or later, it will be presented last month. Anyhow, you can find it on my website. And you may have to iterate in each state of the system development process and over the entire system development process, depending on the type of problem you're solving and the complexity. And that's covered in 2 other papers at the 11th International Conference on System of Systems Engineering. And again, you can find them on my website. So look at the forward, backward, forward. This is how you plan. First of all, you conceptualize a vision of the feasible conceptual future desirable situation, and that's a research problem. You don't know where you're going till you get there. So you've got to conceptualize it. Once you've conceptualized it, you then work backwards, because you know where you've been. So you just figure out how you got there. And that's an intervention problem. Same problem solving block based on Derek Hitchens' outline, but the activities inside each block are slightly different. And so you start with a target, and you know that in order to have a target system working, it has to be integrated. And before you integrate it, you have to test the parts, because you don't really want to integrate untested parts, because then you don't know when the problems are due to the interaction, or the fact that the parts don't work. Well, before you can test the parts, you have to build them. Before you build them, you have to design them. Before you design them, you have to specify them. And then you document it as a forward-looking plan. And you can draw it as a waterfall view, or you can draw it as, and they're the milestones, or you can draw it as a V view. And the V view was designed to show you the relationships between what you were designing and testing at each in the different stages of the system development process. And do you realize that we have educated 2 generations of systems engineers who don't realize that the waterfall view and the V view are just 2 different views of the same process? They think that they are 2 different life cycle models. Well, they're not. They're just 2 different views of the same process. And this is one of the myths that we are perpetuating in systems engineering. And when we're doing the planning of the process, the simple way is, or the way I use, is 3 streams of work: management, development, test, and quality. The work is done between milestones, and it's broken up into smaller blocks, and the whole thing comes together as a project network. Does it work? Yes. And here are 2 examples that have been published in the INCOSE IS proceedings. The Multi-Satellite Operations Control Center at NASA Goddard Space Flight Center. These were done. This one documents the pre-system requirements review activities, and we created a system requirements review that nobody had any questions on, and everybody accepted it in a situation where different stakeholders had totally different concepts of what should be done. And then the Liz Solar Field Command and Control System. This was the world's first commercial solar-fueled electricity generating system. It works in different life cycles, whether they're customer-driven or supplier-driven. Traditional systems engineering deals with customer-driven. We have a need, a set of requirements, and so on. But there's the other life cycle, which is supplier-driven. I have this set of components, so I have this idea. How can I take it to market? They come in all shapes and sizes, macro or micro. And so we need to tailor the problem-solving process. I'm not saying the systems engineering process. We need to tailor the problem-solving process to create the systems engineering process. Some of these products make it to market. Even though we can have perfect systems engineering, many of the products don't. One example was the Terry. This was a desktop computer. It was designed for the executive secretary and the executive, and it hid all the cables and everything inside one very nice looking case that you can see here. This was about 1985, 30 years ago. It was a COTS integration process, and it worked very well. It didn't make it to market because we couldn't get the investment. The mother company needed the funds more urgently somewhere else. So, poor systems engineering produces the wrong solution. Good systems engineering may always not be enough. Your product may not get to market in a supplier-driven environment. But that should not stop you doing good systems engineering. So in conclusion, the systems engineering process is an instance of the problem-solving process. Changing the wording in IEEE 1220 section 4.1 led to some unforeseen negative consequences. Each systems engineering process in a standard is the same problem-solving process, but it was tailored to fit a different situation and the language was changed. Systems engineering are following the same process but may not realize it, because tailoring a process by different people at different times led to confusion and contradictions by other systems engineers who studied different versions of the systems engineering process. We should stop using the term systems engineering process and use the term problem-solving process, system development process, or system lifecycle. And remember, you create the system development process for your situation by tailoring the problem-solving process. Thank you for taking the time to view this presentation. You can find more information on the publications page at the URL and on my YouTube video channel. Comments, I'm looking forward to them, but I'm not holding my breath.